30.
All right. So, let's see. Last time we were talking about. Last time we went over.
Pulse Width Modulation.
That was what we ended with. So the course, we went over the homeworks, the first set of homeworks, which was make lights blink, and I spent a lot of time breaking you in on delay functions and how great they are, but how awful they are, and went into the millis function so that you can make things happen at certain times, and then went into interrupts because eventually you're going to want to learn interrupts. But on an Arduino, using the Arduino IDE, your attach interrupt is only for your 2 interrupt on change pins, which I think is pin 3 and 4 or 2 and 3, I don't remember. And then so I showed example code of, well, if you want to go in and write an interrupt, here it is. And how if you don't write an interrupt service routine for the particular. Do you just hear somebody knock?
Sound like it. Maybe it might be the guys next door working. No.
If you write an interrupt service routine if you fail to write an interrupt service routine for a vector, for an interrupt vector, then it will cause your thing to reboot because it'll run off the end of the table and go through. And then we started to talk. I think we went straight into PWM from that. We talked about servo motors and making LEDs do things, and it took 2.5 hours to go through all the software, and so I apologize for that.
You're on a roll.
So PWM, we talked about it last time, but I'll refresh because it's been like a month with everything going on. PWM stands for Pulse Width, WIDTH, Modulation. Modulation is a fancy word for change. When you modulate a signal, you're changing the signal. It has a lot of meanings depending on the venue. What we're going to do here is, if you remember, we turned on our LED to blink like a second on, a second off. So if I have a signal that's doing this on, off, I have some things that we talk about here. If I talk about the we have time on, we have time off, we have this time is called P, that's your period, and 1 over P is equal to the frequency. 1 hertz, 1 over 1 is 1. It's 2 times per second, 1 over 0.5 seconds is equal to 2 hertz, and so on. So maybe I should call this T sub P, time period. And time period under T on usually is equal to DC, which is duty cycle. So 100% duty cycle is that, on all the time. A 50% duty cycle is this. A 25% duty cycle would be about that, so forth. So we talked about why would you want to do this. So if you go back to the original electronic stuff we talked about, that'll work better. Let's talk about a light bulb. How do you dim a light bulb? You can, well, you know, there's a lot of ways you can do, but you can say, I can use an adjustable resistor, twist the knob. As the resistance goes up, the currents go down, the light gets dimmer, vice versa. Problem with doing this is, let's say this is 5 volts and this is a, I don't know, 1 watt bulb. When this is all the way off, this draws 1 watt. When he's half on, he's about a half watt, but he's doing about a half watt. So you're always using all the power all the time. That's why it's bad. The dimmers in houses with the little twisty thing, they use a device, the class of device is called a Thyristor. So your AC signal, your 60 hertz, 110 volt AC, goes into that device. And that device, I'm going to draw this wrong probably. The symbol is that. Goes to neutral, and hot comes in. And what they do is they do a potentiometer. It basically looks like that. And what happens with an SCR is when this voltage exceeds this voltage, it turns on. And then when it goes all the way off, it turns off. So what comes out on this side, instead of looking like that, first off it chops that off, and then it chops off the beginning until it turns on. Or they use a diac or a triac or any number of diac, triac, SCR. There's a few others. They're all a kind of a Thyristor. If you ever go to an older house that's got those and you put your hand on that, you'll notice that thing gets hot. Again, you're wasting some heat there, but not as much as if it's just a resistor. And then the last thing, not the last thing, but then we talk about voltage controls or current controls and things like that, but they get complex. So the last thing is we can PWM an LED, or even you can't do a fluorescent, I don't think, but you can do a regular tungsten incandescent bulb. They'll do it, but you'll start to hear them sing after a while. So you need to choose a frequency that's high enough that you can't hear it. So many kilohertz. And what this does is a persistence of vision. What your eye sees is not, it doesn't see instantaneous light. It integrates light. So if you see a photo flash, or if you see me turning this light on and off lots of times, it's in this amount of time, these could have the same brightness because I'm going to integrate the energy over time. It's energy landing. How much energy did I get in this amount of time? So we want a PWM. The other reason we want a PWM is because of servo motors. The two main reasons you want a PWM are because of servo motors. We'll get into a third one here in just a minute, but I didn't do anything with that. A servo motor, the way they work, generally speaking, is you've got a DC motor, the shaft that comes up, and most often there's gears. There's several gears, stacked gears that come back. I've got one there on the table. And somehow, maybe there's a potentiometer down here, and then there's, it's usually, so it's a DC motor, And remember we talked about an H-bridge, I think, at one point? Did we talk about an H-bridge?
Don't remember.
Don't want to go there yet. I'm going to go there now. An H-bridge is a way of steering current. If I have a standard DC motor, if it's got 2 leads, and if this one's the one normally called plus and this one's normally called minus, for instance, that will cause a clockwise rotation of the shaft. And if I reverse them, then I'll get a counterclockwise rotation of the shaft. So that's how I can make a DC motor go both directions. You can change, what you do is you use what's called an H-bridge. These are FETs, but I'm just going to use switches because that's how you use the FETs. And I'm going to use ground here and some voltage here. And we'll have in one so I've got 2 switches, and then I've got N2, I know we talked about that. That's an inverter signal. So if that's high, that signal there is low. An inverter takes a high, turns it into a low, or takes a low and turns it into a high. So what happens is if this is a 1 and this is a 0, then this one's on, and that one's on, and that one's off, and that one's off. So current flows. I'll draw it that way. And I get clockwise rotation of the motor. If this one becomes a 0, and that one's a 0, then he's off, he's on. So what I've got here is I've just got both sides tied to ground and nothing happens. And now if I make him a 1, now he's on, and he's off. And now current goes this way. And now I get counterclockwise rotation. Very simple way. If I make both of them the same, either they're both high or they're both low, then I've either got 5 volts on both sides or ground on both sides. The motor doesn't turn. There's nowhere for current to go. It's called an H-bridge because it looks like an H. So, take a DC motor, you hook its shaft to a potentiometer. So this is, as you turn the knob, it basically moves up or down the resistor. So the voltage, this is a voltage divider. Remember we did voltage divider equations on like the first or second class. So the voltage changes. As you wipe it up, voltage goes up. As you wipe it down, voltage goes down. So as this thing turns that shaft, you know where it is. You get a specific voltage out. And then there's a little control circuit over here and an H-bridge. And the H-bridge wants to turn the motor left or right. The control circuit monitors whatever the feedback is and said it's in this position. And you tell it, I want to be in that position, and if it's not there, it will drive to there. And then it'll stop. And then if you push on it, it's going to say, oh my God, I'm not where I'm supposed to be, and it's going to push it right back. A servo is short for servo loop. It's a closed loop control. And there can be things besides just, oh my God, which would be purely proportional control. You can add in integral and derivative control to change the characteristics of how they act. And that's an important thing inside of control systems. We won't go into that here. That's like advanced topics stuff. But why am I going to this? The way you control most servo motors is with a PWM. That may be a lie. Every servo motor I've ever used or built around uses a PWM control. I don't know about what's used in a CNC or something like that, but for like remote control cars and remote control airplanes, little servos in there, this is how they work. They're not all this signal, but they seem to mostly be this signal. This period, T period, actually frequency, I guess I should say, is 50 hertz, which is 20 milliseconds. 20 milliseconds. And these little guys right here, you'll be able to see that on the screen. I put a flag on it so we can see which way it turns here in a minute. They can only turn 180 degrees. So if I've got that motor right here and I put a stick on it like a speedometer, it can go from minus 90 degrees to plus 90 degrees. Minus 90 degrees is minus 90 degrees is 0.5 milliseconds. 0 degrees is at 1 millisecond. And plus 90 degrees is at 1.5 milliseconds. I think that's right. It might be 1, 1.5, and 2. I've got it all in my documentation. Look it up for your servo motor. But most of them is this. So that's why you would want to do PWM. So last time I gave you a software, I gave a software example, and then I went home and coded it up and it didn't work. I told you it might not work. It did work, but it didn't work. So I told you, let me pull it up right here, coded PWM. I said, I'm going to use pseudocode, write bit on delay count, write bit off, and then delay. I said 255, I think, minus count. And then count plus plus, increment count. And we were going to take advantage of the fact that it's a byte and it'll roll over at 255 and it would work. Problem is the Arduino delay function is in milliseconds. And so if I turn it on for 1 millisecond and then I turn it off for a quarter second, it's and what it does is you see this weird blinky pattern where but you can actually see it. It's too long of a time. So I did some research and the right answer was change delays to delay microseconds. And delay microseconds. And then I had to do some checking on count because
I didn't.
I did.
16,380 minus count.
I think you told us delay microseconds because I actually have delay microseconds on here already.
Yeah.
Okay.
But I didn't. So you might have said it, but written something different. So I might have copied what you wrote, and she might have copied what you said.
I wrote it on the board as this, and then I think I went back and thought about it and said, milliseconds probably won't work. It probably needs to be microseconds. But when I was running through, I was skipping through, so I didn't hear all the stuff because I was trying to remember what the heck was the homework anyway. So, and I used 16,380. So increment count, if count greater than 16,380, count equals 0. And so that's 16.5 milliseconds, which is a lot faster than I can see. That's 200 hertz, or a little bit faster than 200 hertz. And there was a reason why I used 16,380, and I think it's because delay milliseconds falls apart just a little bit above that. Its register size, I think, is 16.5, whatever, 12.
Yes, 16,535 or something like that.
16,535, which would be 8. Is that 16 bits? That'd be 16 bits, I think. So yeah, that's 16 bits. So if you tell it one more than that, then that's the same as being 0, or 1, depending on how you do your math.
So instead of relying on it hitting that, you're just setting it to 0 manually.
Yeah, I set it because there is some weirdness in things that go on. If you read the documentation on it, it says you can't really go a whole hell of a lot slower than this. And well, they don't really tell you that, but if you do your own stuff, just the time to go into the call, do the setup, and come back out.
Right.
About the minimum you can really do is maybe 10 microseconds or something like that, 5 microseconds. So there's some weirdness, but what you see right here, so we can watch me. So make sure I'm not telling a lie, and the whole world can see me load up that one. Turn that so there we go. So that's exactly what I said. So digital write, output pin high, delay microseconds count, go low. And if I write that to this little Arduino here, you'll see that orangish yellow LED start to go through this, and you'll see what I was talking about before. It doesn't just, there we go. So you see it get brighter and brighter. There we go. So that's as fast as I can do it. And if you put a scope on that, you'll see that pulse width changing. You'll see the duty cycle going from 0%, or practically 0%, out to almost 100%, and then popping back.
Not to get on too much of a tangent, but where would you put the scope on there? Like just right on the LED?
I drop it right on the LED, or I drop it here on this side of this resistor.
But essentially on the two sides of the LED, or
No, well, you reference to ground.
Okay.
You have well, you don't have to reference to ground, but usually you do. So it doesn't matter where you put here. If you go here, you're going to see a 5-volt signal. If you go there, you're going to see probably a 1.2 volt signal. So
cool.
If you do that with a scope, you'll see it run across there.
Cool.
So that one's out of the way. What I need to do is put these up online so that they're available. I was looking at my website the other day, and so the next thing.
Put it on GitHub. Everyone loves GitHub these days.
I actually have my own website that I haven't updated it in a while. So the next thing, since we're using Arduino, if you're using an Arduino, they have a built-in command in their libraries called analog write. And I think we touched on this at one point. Maybe when we were, I know we touched on it because we were looking at our Arduino boards and seeing the pins that have the tilde on them. Mm-hmm. A pin with a tilde, thank you, which is on an Uno is pin 3, 5, 6, 9, 10, and 11. Those are the only pins that you can do an analog write on. I think that's a lowercase. Pin value, I think.
10, 11, 6, 5, 4, 3,
9.
6, 5, 3.
And the value is a range of from 0 to 255, I believe. Excuse me. You guys understand this, right? The brackets?
No, it's like an array or a list.
No. Okay, so when you're talking,
it's a range for you.
when you talk, well, it is for arrays. So
Okay.
if you say 0 to 255, let's do this. If I do this, this means 1 to 254.
Okay.
If I put, so that's a soft bracket. If I put a hard bracket on 0, actually 0 comma 255, then this goes 0 to 254. I'm writing in a stupid angle here. So a hard bracket means that that's inclusive. This is a mathematical notation.
Okay.
So I'm mixing a mathematical notation in, which can be a little bit confusing because it looks like array stuff too.
Square bracket down there, and one of those is probably 255, not 254.
No, square and a soft.
Oh, okay.
So you got
So
a hard and a soft.
Oh, okay.
That means
Oh.
up to and including, and this
Gotcha.
means up to,
Okay.
basically, or down to, depending on the side that it's on.
Okay, sorry.
So as a pure mathematical notation, so there's four possibilities here, right? There's 0 comma 255, hard 255, which would be 1 to 255, and then there would be both, which would be 0 to 255. So you see the four different,
Gotcha.
you're bounding the range. So I think that's right for, you have to look it up yourself for the analog write. The analog write uses it depends on which pin you use, if I remember the reference correct. Like if you go to arduino.cc, under the learning, there's like 4 tabs across, or 4 clicky points. I think one of them's learning and it has reference, and it basically has the reference library right there, the standard reference library there. And if you go in analog IO, read about analog write, I think it uses 300 and some odd hertz on one pin, and it uses 1200 or something like that on a different set of pins. The reason that is that timer 0 and timer 2 are 8-bit timers. Timer 1's a 16-bit timer. So it limits, timer 0 and timer 1 can only run a short amount of time before they overflow. So analog write was written absolutely in mind of doing exactly what we're doing here. So this little piece here is analog write, and then it's delay 100, so for 100 milliseconds, and then value is count, and then it's count plus plus, and it's a byte count. So here we're taking advantage of the fact that it's a byte, it's 8 bits. When it hits 255, when it plus 1s again, it'll wrap over to 0. And it'll be a tenth of a second, should be a tenth of a second between each one. So I'm bringing this down here again, zoom in. this visible for the whole world. And we'll load it in. I'm set up on pin 3 again. Pin 3. Using pound defines like we were talking about before. I've been reading a little bit on this. Pound define is kind of deprecated. They prefer that you use constants. So did that go through there? Now you notice this one takes a lot longer because I'm delaying so long in between. I'm not sure what I just did. I just hit the power button.
Barely even touched it.
Maybe
Did you
accidentally.
hibernate it?
Hello. I may have broke it. Did I break it? I have no idea what I just did.
Might be going to sleep or something. There's some
There.
lights.
There we go.
Okay. Might have had to finish going to sleep before you could wake it back up.
There we go. All right, so we see 255 at... I must be hitting the freaking power button. This thing's... The USB cable's pulling me out of the way over here, and I hit the power button again. Okay, looks like I'm all the way asleep. What's nice to notice, though, is the USB power is still turned on when it's asleep.
For now, it might. You might not have let it go completely to sleep.
No, I'll tell you, it's interesting. My machine at home, my desktop, I can turn it off.
And USB still gets power.
And USB has power until you do something, like if you unplug it and plug it back in, then it won't be on anymore.
Yeah.
There's some sort of little weirdness going on there in the hardware where it says, "Oh, I still need to."
Yeah, I know. I know some machines will do that so you can keep charging things when you shut your machine down. But
So 255 times 0.1 seconds is 25 seconds. So that should be about 25 seconds to go from off to full brightness. And so there it goes. And you'll see it gets, again, it kind of gets bright, it's kind of dim, and then it brightens up rapidly, and then it seems to get bright really slow. And that's because we're giving that light, that LED, a linear response. It's putting out a linear with time response, but our eye sees logarithmically. So if you see an exponential output, your eye will flatten that out into a line. And so across 5 bits, there's actually only 13 steps that are equivalent up the line, if you break them up relatively evenly. All right. Did you know I need to quit? I've got a touch screen. That's part of the problem here too.
Yeah, I keep forgetting mine is a touchscreen.
So that's the analog write homework. So the next thing, there is a function called tone. And what tone will do is it will give you a square wave at a specific frequency. So you can't really drive a... I've got tone on pin 3. Do you have in your little maker kit, do you have a piezo? A buzzer?
Maybe. It's actually out in the car.
Yeah, I don't have one at home, so I couldn't plug one in to play with it.
You wanna? Sorry, I left it out.
No,
there.
it's all right.
Sure I needed it, but you can grab it real quick.
You can't...
by the time you get done objecting, I'll be back.
Okay.
I don't know that this will work because I couldn't actually. I don't have
You
one to
couldn't
play
test
with.
it?
I couldn't test it. I've lit it up and I can see that it flickers the LEDs and does weird crap fairly quickly. So let's play that. That's on pin 3. So this is tone, and basically the only difference is instead of analog write, I'm using tone.
This isn't one, is it mine? I don't think.
That might be mine.
It's yours. It's probably that one. pictures on the lid.
Passive buzzer, active buzzer, one piece. Okay. Is that what that is?
Little barrel, guys.
Looks like it. You got pots in here, you got LEDs, you got
I got all
transistors.
sorts of junk.
You don't have junk, you got fun stuff. Or junk, whatever you want to call it.
RFID.
Remove after washing. No, we're not going to wash this. Did I not? Yeah, this takes too long. Let's do this.
I think the heat is just blowing cold air.
Yeah, it verified heat is on.
It's okay, I got your jacket
It
now.
was set at like 60s.
I don't know if this will work. I don't think so.
Is it getting louder or is it just my ear?
What you should do is hear the tone change. So, and I've got this on a long delay, so let's delay 100 instead.
I mean, it sounds like it's modulating.
Whoops. It's going to be all sorts of screwed up. Delay 100. Delay. All right. So we're sweeping through it pretty quick, and there's only certain frequencies that it can handle. The tone is made. Tone lets you play a tone. It's a square wave. So one of the things you gotta. That's gonna get really annoying really fast. So I'm gonna go ahead.
It's like one of those Halloween toys.
Yeah, I'm unplugging it now.
The rat.
So you can read it. You can read up on tone. Tone is basically the reason you can only do it on these ones with the tildes is because they are the ones that are attached to the hardware timers, and I will talk about those a skosh tonight. Yeah, we've been an hour. I've got enough time, I think. So. What it's giving you is a 50% duty cycle square wave at the frequency you tell it. And there's like a minimum and a maximum frequency, and I don't remember what they are. How do I put this? A signal that you would see is a combination of signals. DC is every frequency at the appropriate levels that it makes you one. A tone is a single frequency. It's a sine, but we're talking frequencies and sine waves. When you make a square wave is the fundamental frequency. So if I say, I'm going to use an easy number, 10 hertz. A square wave has a fundamental of 10 hertz. So here to here is 0.1 seconds. It's also all the odd harmonics. So it's also 3 hertz. It's 30 hertz. 50, 70, 90, 110, and so on. And you can, I can see the look of doubt on your face. If you go into Excel or an equivalent program, and you go across the top and say 0 to 360, so that you've got 360 points of the sine wave, right? And you say sine of it's been a while since I've done this. If you do it so that you get the frequencies, so you get one frequency and so you get sine of 10 hertz, right? And maybe sine of 30 hertz. And you want to run them off for each one of these so that they compress in, so that you'll get this one, and you'll get this one, and you'll get this one, and you add them all together and graph them, you will get a square wave. I remember the first time when I first learned this in school, I was like, no way. And I went through and did it, and I'm like, what? It starts to ring. I mean, you start off with this first one, and then when you add the third harmonic, it basically comes here. So now you get this thing that kind of looks like that. And then the fifth harmonic comes in and does that. So you kind of get this mess, right? And each one adds a little bit more to the signal and perturbates it until you, and the more harmonics you get, the sharper these edges get. That's easy when you're talking 300 hertz. When you start talking a megahertz and 10 megahertz, you start running them through lines. When you look at your scope, and remember when we were doing the button clicks, and we saw some of them kind of went like that. That's an oddball frequency out there. It's impurity of your signal, and it has again, I'm lying by simplifying, but it has to do with phase delays. Has to do with different frequencies traveling at different speeds through your wire. It has to do with imperfections in the wire that cause reflections, where they actually bounce back at you and then get superpositioning. So crazy crap, but if you got to be, this is one of the things you got to be careful with especially digital oscilloscopes, because they sample at a certain rate. And you can get the wrong signal. You'll look at it and say, oh, that's this signal. And really, it is a harmonic of what you're supposed to be looking at. And again, I've been pointing down there instead of up there, but there wasn't anything important up there, I don't think. So that is tone. And what do we have here? So there is, if you go... again, if you look in the reference, there is a servo library, but we're going to talk about how the servo works first. I think we talked about this last time. So first off, you have a counter. You have compare A.
I don't know who it is.
I think it's Rose. Just the bag off the chair. Hey, you can move that if you want.
Hey,
Hello.
how are you?
All right. How are you?
You were at the first class, right?
Yeah.
Long time no see.
Yeah.
Boy, good thing there's no attendance on this.
I know.
I just go around feeling bad that nobody cares.
No, we all care.
Told them we care. Also told them that trying to learn as much as we can so we can teach other people.
Yeah. What do we Pulse Width Modulation?
Servo.
Yeah.
Yeah, okay.
So we've just been doing lighting LEDs and making them change position, or I'm sorry, brightness. Talking a little bit about the tone function, sticking with pure Arduino libraries and how they work, but also showing how other things work. And so the first thing we did was a coded PWM, where we actually wrote code to do a PWM.
Yeah.
And now I'm getting into the actual hardware, say this is what this hardware does, and this is why you can only do it on these pins. When you do analog write, we did an analog write also.
Okay.
So there's a couple of control registers that you set up back here, but you got 9 and 10, I think. So let's choose pin 9 and let's choose pin 10. And these are wrong, but so the first thing you can do is the control registers can tell what the outputs of these things to control these pins directly. So we talked about this before. If I look in time, this is if that's 9 and 10, then this must be It's not a counter, it's a timer is what they call it. And so this would be timer 1, which is 16 bits, I think. And this would be OC1A and OC1B. And I think B connects to 10. So one of the modes you can do is anytime this count matches that count, so there's a prescaler and there's a system clock out here. I'll draw it this way. System clock. 16 megahertz on an Uno. And the prescaler has a series of dividers in it. So you can say your choices are basically no clock, so turn it off. That's great to save power, because if this thing's sitting here running, it's using power. And when you're doing micro power type stuff where you want things to go to sleep and use nothing and run off of one little stupid coin cell for a month, you need to shut down everything you can. There's clock divide by 1, so clock goes straight through. There's clock divide by 2, clock divide by 4, clock divide by 8. 1, 2, 3, 4, 5. Clock divide by 16 is 6. Clock divide by 64, I think, and clock divide by 128. The 3 timers are different. They have different numbers. But you can, so what happens is you take 16 million, divide by 2, then I've got 8 megahertz going in here. If that's 16-bit, it can count to 65,535. So the time to fully, for this guy to count, all the way up to 16,535, and then he'll wrap around, right? We talked about the hardware. He'll just count, wrap, count, wrap. So he'll do this over and over and over all day long. So 8 million this time here, your period would be 16,535 divided by 8 million. You can do the math. I can't do that in my head. But I also created a spreadsheet. Remember, we worked with the spreadsheet a little bit and said, just figured that stuff out for me. So now I have some choices with my timer hardware. I can say anytime that this and this, that's an AND symbol, anytime they are the same, I can make something happen. So in my hardware, I don't usually diddle timer 1, but I can write in my C code, I can say OCR1A equals some value. And it will write it directly to that value, or right into that specific piece of register hardware. So I can say, hey, if this is equal to, let's choose an easy number, 8K, since that's half. So whenever this is 8K, I can tell it to toggle that bit. So what will happen is it'll go, book. Let me get a different color. It'll come up.
I think that one was Dad's last time.
Yeah.
Did it not get thrown away?
It will come up. And then the next time that happens, it will toggle down. So toggle just means change the value. So now I've got a square wave that's going on at 32K divided by 8 million, right? It's half. The period is half. It's 2 full cycles. And I can do that with both of these. So this one also has its and so I can put a different one in here. I can say, let's make this one, are those registers 16-bit registers on that one? I think they are. So let's make this one 16K. And so this one then will go, it'll come here and it'll toggle, and it'll toggle, and it'll toggle. Or I can make it 2K, and it will come here and it will toggle there. And then it will toggle there. And you see what I'm doing? I have the frequency has stayed the same, but I'm changing its position in space when things happen. Not something that you would normally do, but it's there for you to be able to do if you want to. The next thing you can do is you can say, I don't toggle. You can choose a mode, and the modes that you'll use most often, erase all this green, one of the modes that you'll use most often is you'll say, when this value is less than that value, I want him to be turned on. When this value is less, let's see, when the timer 1 is less than this value, I want the pin turned on. When the timer is equal to or greater than this value, I want the pin turned off. So with our example of 2K, what you'll see is this. I've just PWM'd this, right? Because now if I put 4K in here, that is a 4, I swear. Now this has moved over here somewhere. If it's 8K, then it comes halfway. And if it's 16K, it's right up to the edge and it might turn off for 1 count and then come back on. That's what's going on in the hardware for PWM. Analog write uses this. It uses this hardware. It's the reason why you can only do an analog write on the pins with those tildes on them, because the tilde tells you it's hooked into one of these. Now you can also play a game. You can't do it, is that right? I'm going to say this, I'm not absolutely sure it's right. You can do this on OCXA, but not on OCXB. If the count is the same, reset it. So now by changing this value, you can change the duty cycle. Or not the duty cycle, I'm sorry, the period. So right now if I say reset the timer on when it hits 8K, now it only gets to, let's redraw it. So if I had it at 16K or I didn't do anything and just let it run and run and run, I would get this, right? With that being 65,535. So if that's 16K, then 8K would be right about there. So now if I set that to 8K, what's going to happen is this. And now you just see I doubled my frequency. And then I can still play the same game here. Oh, well, if this is 4K, now it's on this amount of time. But if I was doing the long one and it was 4K, then it would have been whoops. Man. Yeah. Like that. So we can see that we have the same pulse width, but I have a different frequency, which means that my duty cycle basically doubled, or actually quadrupled, right, because I have the frequency doubled, I guess, because I'm not very good at drawing on the board, and this may or may not be to scale. So that's what's going on there. And I think the servos, you can get, because remember we talked about the servo signal wants 50 hertz, which is 20 milliseconds for the duty cycle from here to here, and then you only vary this between 0.5 and 1.5 milliseconds. So we'll show that here with the servo. Bring this down so everybody can see the magic we're getting ready to do. And see the code on the board maybe.
They might have misled you. I think it's 16384.
or something.
Yeah,
65535 would be the 60. As soon as you said 65, I went, oh, that's the 65535. Doesn't matter.
Let's see, we'll put it on the left. Again, so we can turn things off. So, if you use the Servo Library, you up here at the top, if you look, you'll see I wrote pound include angle brackets servo.h. .h is a header file. Servo is the library that's going to call. You can type that in yourself if you know the name of the libraries, or you can come up here on Tools, no, Sketch, Import Library, and there's a whole list of libraries that come with the standard distribution. There's an audio library, there's an Ethernet library. We might do Ethernet here before too long, or just to show basic connectivity. If you've got a wireless, they make wireless shields, they make Bluetooth shields, and everybody has their own library for their piece of stuff. And if you read on the Arduino site, they talk about how to import a library that's not one of their standard ones that somebody else wrote. So, but you import it in, you make it available here, and then you got all these different things that you can use. So, servo on pin 9. So we've got the servo, and that should, like I said, I did not have a servo at home to play, so there we go. So we're counting, and we talked about it goes between plus 90 and minus 90. And so this is just using the servo library, and to use the servo library, this was really easy. This was it's 1, 2, 3, 4, 5 lines of code. And then up here where you say, if you include those two, 7. So you have to say servo. This is a C++ statement, so you're instantiating a class. And so you say, give me servo, give me an object, a servo object. I named it servo. And all you got to do is a servo write and the count is anywhere from 0 to 180. Where 0 is all the way to the left and 180 is all the way to the right. And that's their library. To show the hardware, if you want to get into it, I actually wrote it up the hard way. So I've gone and defined pins. I'm going to put it back on pin 10 because that's where I did my library stuff on. I've defined my minimum and maximum values. So for if you set this timer up at 50 hertz, then it's 2,000 to 4,000 counts is the right number. And if you come down here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines just to set the timers up to be able to do this. And then there's another couple of lines of code where I do some math to say, oh, when I'm at this many degrees, that means my pulse width needs to be this. So it's basically a slope offset math calculation. So that tells you that the whole servo library is about 15 or 20 lines of code for a servo object. But if I load him up, so there he goes, doing pretty much the exact same thing as before, only it took me 30 lines of code because I didn't use their library. If you use their library, so using somebody else's libraries is a great way to get stuff done quick.
Mm-hmm.
Sometimes they don't work. And then you're set with trying to figure out why the hell things don't work. I'm going to make a quick statement about running a servo directly off of your Arduino. He's not doing too bad. That chip right there is the voltage regulator. Since I'm running directly off the USB, it's not going to get hot. But that steps your 9 to 12, whatever volts you got here, down to the 5 volts for the board. And that's a linear, so any power you're using, any current that you're using gets multiplied by the change in voltage, and that's power lost there. One servo is enough to make him get pretty warm. These little servos that you can, these are dirt cheap. These are $5. Maybe, in fact, they might only be $1.50. These draw 1/4 of an amp, which is half of what USB says you can have. So I'm drawing half my USB right here on this guy. For this little bitty guy right here. So be warned.
He's not even doing that much.
So if I do one, I can do this just fine. If I put a second one on here, you won't you won't break your computer, but what'll happen is there's a current shut off in there that says, oh my god, that's too much, and it'll just shut you off. And then your stuff won't work. And then you'll be wondering, why doesn't this work? And it's because you're drawing too much power. And that's all we're going to talk about servos and PWM tonight. And I'm going to unplug this guy. Next, we're going to talk about stepper motors. There's a great YouTube video that explains how they work, sort of, and a lot less detail than I might go into, but I can't give you the address off the top of my head. I can't write it up here. What I used it for was he was describing the waveform so that I could just copy off of his instead of having to sit down and figure it out in my head. So a stepper motor just to get, I got to draw the inside so you can understand what's going on, I think. I think I need to. A stepper motor has the rotor shaft, I'm going to draw this really stupid. This isn't physically accurate. This is conceptually what's going on. Let's put it that way. Boy, that's supposed to be round. Do this. I don't know if there's even numbers. We'll just do that many. North, south, north, south, north, south, north, south. So the shaft, the rotor, the part that turns, rotates, rotor, is basically a bunch of magnets. And they're set up so that you have a north pole and a south pole. There's it's an alternating pattern. And then what you have is you have a set of coils that comes in and basically makes electromagnets like this. And all of the souths are tied together like that. And all of the norths are tied together. And then they each have their returns that come back out. So north return and south return. It's actually two different halves, is the way it's set up. And then there's usually a center tap that hits in the middle of these things. We won't go too deep, but what happens is if I energize south, if I make this a high, then this is going to be a south pole, and it's going to repel the south, but it's going to attract the north, and he's going to go, and he's going to take one step, tick, over. And so now what I can do is I can go, it's a 4-phase system. It looks kind of like that. So when I hit this one, it's going to align here. When I hit the next one, it's going to align like halfway, or it's going to do 1 step, 2 step, 3 step, 4 steps as I go through this. And so 4 steps takes me a full revolution. What you'll normally see, so this is called the wave mode. So this runs, it's very easy to program. It doesn't have very much torque because north is turned off, south is turned on when north is turned off type things. So only one of them's active at a single time. What you'll normally see is called full stepping. So this turns on the north and the south at the same time, and bang, it steps. It's still only 1 step. It uses a little bit more power, uses twice as much power, but it's got a lot more torque. It can move a bigger thing. It can hold against a stronger load. And then there's a game that you can play that's called half stepping, where you do it takes 8 phases instead of 4, and it does a number where this guy comes on no, do it this way. 1, it's 1, 2, 3, 4, 5, 6, 7, 8. So he'll come on like 3, and go off for 3, or no, only 3. He stays off the rest. And this one, 2, 3, I think looks like that. Yeah, I think that's right. And then this one comes on for 3, and this one comes on for 3. So I've drawn it slightly wrong, but what happens is, you know, you get here, nothing else is on, you get that first south that gets you partway there, but then south and north are turned on, and the way it's wired, it actually moves a half step in between, because it's being pulled by this one, but it's also being pulled by that one, so it goes halfway in between. It doesn't know which one to go to. But then the other ones are being repelled equally by all of them. And then you get to the next one. So it's like a combination of a full step and a half step, so it moves in half step increments. You don't care. This is what's going on. What you're going to find is a servo controller. There's 2 different kinds of servo controllers. There's one that has 4 lines in and 5 lines out. 5 or 6. Assuming that it's a unipolar stepper motor, which is what this is, center taps are tied together. I was going to bring those. If you go to, I'm not sure, Amazon or eBay, which one it is, they sell a little box. There's a company, it's called Ebu or something like that. The box is maybe
Elegoo, because that's
Elgoo.
all our stuff is Elegoo.
Okay, yeah, it's the same company. So the box is just a little bit longer than this, maybe a quarter again as long, and maybe twice as wide this way. In there, they have a stepper motor that looks like this. If you look at it from the front, from that way, it looks like a Cyclops. Actually, it's not geared. It's got a key on it that way, with the tails coming off, and a little board with this driver chip on it, and I think 4 pins.
I don't think I have that.
4 pins. You might have one in there.
Yeah, I think it was a stepper.
Servo Motors.
You got a servo right there. This is it right here. This is exactly the servo. So I drew it kind of right. And there's a little board in there that should go with it.
There's this little board here, maybe. That board, there's this little board.
That's it right there. So this is the oops. So this is the board. So this is the first style of stepper motor.
Those little ziplock.
It's rare that they actually have one that locks so well.
What's the difference between a stepper and a servo?
Okay. So I just showed you how a stepper works. I just showed you how a stepper works.
Right.
With basically electromagnets moving
Yeah.
around. A servo motor controls a DC motor, controls the direction, and you tell it the position it's supposed to be at. And it drives to that position and it stays there. So if I want to go from here to here with a stepper motor, I've got to go step, 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 step. If I want to go from here to here with a servo, I change that PWM one time to what I want, and it'll bam, and it'll go there.
And that's the servo.
And that's that one right there. So you saw how I was doing this. It would go tick, 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 and then it would zip back.
Right.
That zip back, I just changed the value from 180 to back to 100, back to 0, and it bam, went right back to
So
0.
it knows where it is in space, and this stuff
Whereas
doesn't.
this doesn't.
Yeah. Okay.
But there are reasons why you want to use one over the other. Servo's quicker? Well, a servo is not necessarily quicker. A servo is not as precise. A servo, generally speaking, does not have the same kind of torque. The servo, there's different uses. You know,
Servo is good for steering an RC car or adjusting a RC sailboat. You know.
but you
sail
wouldn't
or
use a
whatever,
servo. Most servos can only go minus 90 to plus 90, whereas a stepper can step forever and
Right.
keep going. So, and with a stepper, the servo has a feedback of where it is internally, unless you have a big system where you're controlling it and you know.
Right.
So you can tell it to go there, and you know that it's going to go somewhere close to there. But then, no matter what happens, it's going to drive and try and keep itself there. Whereas a servo, I can say step, 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 and I can count 50 steps, and I know that you should be at step 50 now. And I can go away, and it will lock. If I've got the currents turned on, nothing. You have to be able to overcome that current and torque to be able to move it.
Right.
Now, but the
And
servo.
you misspoke. A servo. You said servo when you meant stepper.
I keep doing this. So with a servo, I've got the instantaneous feedback control of where I am.
Right.
When I get there, I shut it off.
Right.
So I can easily move it a little bit. But as soon as I do, the servo loop's going to kick on and say, oh my God, I don't want to be there, I want to be here.
Right.
And so you don't have to move it very much for that servo to kick it right back.
Yeah.
But then it's going to turn off and it's going to sit there. And so you can get things, especially if you're running low and your batteries are low, you start seeing servo jitter where they start going like this.
Right.
Okay. Now with a stepper, if I leave power on it, once it gets to there,
Right.
I can
It's
overcome that. Well, I can overcome it. If I overcome the torque and cause it to skip a step, it'll skip a step and I won't know it. But it's got pretty considerable torque to get there.
there. Yeah.
Whereas with the servo, if I push it past, well, as soon as I let go, it's going to come back.
Yeah, you have all those tiny little electromagnets, so if you can get it from one pole to the next step.
Then it's going to skip right
Yeah.
over it. You're going to be skipped a step.
Um,
So the other thing, so one of the drawbacks again with a stepper is I have to go through all those steps. And if I go too fast, I can basically causing the magnetic field to rotate, right, and push it along with it. I can go too quick, and it won't overcome the inertia of the whole system on it.
Right.
So that's why if you look at 3D printers, if you set them up to go too fast, they'll start missing steps.
Mm.
That's why you're going faster than that.
Yeah.
You're moving the field faster than you can move the hardware.
Tend to use a stepper motor on X, Y, and Z, and like on mine, X and Y are belts, and then Z's a lead screw, or what do they call it? This whatever. But then you also have a stepper motor feeding the filament in. But since it's a known quantity for what each of those steps are, you can control. I can move 1 micron this way, 1 micron this way, and or up and down. You can move tiny amounts pretty precisely.
Yeah.
You can't get that precision out of a servo, out of one of these kind of servos. A lot of the CNC mills, like a Bridgeport, if you buy the servo system for those are actually DC servos.
Yeah.
And they're using the DC servo because they can turn it fast and get it to where it needs to go, and then slow it down.
It's a lot more travel.
It's a lot more travel. There's trade-offs between the two. What you want to do. The deal with a servo is to get a good servo loop for a real control, like you'd want on a CNC mill.
Yeah.
There's a lot of software with that,
Yeah.
because you can't just go and stop. You got to speed up. You got to do a trapezoid. You got to speed up, get things up to inertia, get to that point, and then you got to slow down before you get there. And with a stepper, you just go tick 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 tick, and eventually you get there, but it gets there slower. But you don't have to change speeds, and some steppers can move really damn quick. So you start getting into price points. What do I want to do it this way, or do I want to do it that way? Well, if I want to do a servo, if I want to do a real high power servo, then I have to build my own complete control loop and all the power electronics for it, and that's going to be expensive. Or I can do a single stepper and a single stepper controller, and it'll handle most of that for me, so that's cheaper. There's all sorts of trade-offs.
Yeah.
Just like any engineering activity, right? You're not looking for the best solution. You're looking for the one that meets your price and the one that meets your requirements.
Right.
And there's 50 ways to get there from here. So that's the big difference. So this guy, like I said, you can buy a box of 5 of these for $13. It just plugs in there like that. And then you bring 4 flying leads off here that are the four phases of the cable. And then you bring 5 to 12 volts in on that pin right there. And you take your ground off of that pin right there. And these LEDs light when each phase is lit. And I know this is exactly how you do it, because like I said earlier, for a change, I actually did the homeworks ahead of time this past weekend or this week. So I've actually already been spinning motors. Let's see. This particular motor has a 64-to-1 gear reduction from the rotor up to the shaft. I think it's got 4 gears in there, all stacked up, all cute. That means to get 1 rotation, 2,048 steps. So that's the kind of precision I can get with this.
And you can stop at any one of those 200.
I can stop at.
2,000 points.
I can go 4,096 steps. Right. This kind of
have
servo
steps?
can only go plus or minus 180. This, I can just have it spin and spin and spin all day long. And I can tell it to go 10,000 steps, and it will stop when it gets to 10,000 steps. And I was sitting there, I was just basically putting my thumb on it like this as an indicator for me to count turns and everything else, and watching it. And at least as far as the eyeball and the thumb feel goes, it was stopping in the same position every time. I'd go forward 4,000 steps, 1, 2 turns. Now go back, 1, 2 turns. Best I could tell, it was stopping in the exact same position every time. Within the slop, I mean, you can feel
there's a little bit of play.
There's slop in there. There's backlash. Now the other kind of controller that you can buy. So these are cheap hobby controllers. This, you would not make a 3D printer out of this. It just does not have the torque you need. The other kind of controller, I've got some of these at home that I'm using. These are big. They can drive 3 amps on each coil. That little guy can draw, I think, can drive a half an amp on each coil. You can buy these on eBay. No, I'm sorry. You can buy these on Amazon for about $14 just for the controller. Or on eBay, if you look around, you can get them for about $6 or $7. And have you ever heard of Marlin P. Jones? Remember Marlin P. Jones? It's a website. They do surplus. And sometimes they've got a lot of stuff that you can look at. It's like, wow, it's a bunch of crap. I don't really want that, this or the other. But every now and then they run some really good deals on stuff, including cheap Chinese benchtop power supplies. I picked up 2 0 to 1 amp, 0 to 12 volt power supplies for like $30 each. And they're decent enough to do anything you want to do on your bench for the most part. But these things, these more expensive ones, I want to draw this. They look like this. I'm trying to draw 3D pictures. What I'm trying to do from the end. You making fun of my picture drawing, my mad picture skills?
I was just being
Smart ass.
yeah,
That's okay.
As we all are.
an engineering, an engineerist. I was saying that electrical engineers can't
Draw all the shit.
Yeah.
They look like this.
You're getting it.
It's been long. I've actually had technical drafting class, but it was 30 years ago. Back in the days before computers. They look like this. They have 2 big Phoenix connectors on top that stick up like this. And one of them is to wire to the motor. So you wire the 4 phases in, 4 phases in directly, and then it wants 9 to 24 volts. And then on this connector, they're opto-isolated, and it's got a big honking heatsink on the back. The thing is, I was going to bring one along with those, and I forgot. It's about that big by about that thick for the whole thing. It's just over an inch thick by about 4-ish by about 3-ish. It's got screw mounting holes here, big heat sink, and this one has 3 inputs. But
How's the drive shaft oriented?
now this is just a controller.
Okay.
This is the controller, but this can control big motors.
Right.
This can control like NEMA 27s, big stepper motors. I probably just wiped a bunch of black shit on my forehead, didn't I?
You're alright.
This guy uses 3 signals and returns because they're basically internally opto-isolated. So you have to bring in 6 wires to be able to control it. One's a hot, one's a ground. So usually what you do is you just wire all the hots up together and then bring off 3 signal wires. And one is enable, one is direction, and one is pulse. So if it is disabled, you can just turn the motor. The coils are turned off. You play with it all day long. You sit there and spin it by hand. If you've got your 3D printer up and that you've home built and you've used this kind of controller, and you're futzing around and troubleshooting it, and you're wondering why the hell is the head ending up here, you can actually just grab the head and drive it back, and it'll back drive everything, and everything will be happy with it.
Yeah, I think on mine there's a G-code command for enable, disable, so you can do that.
Yeah. On mine, when it gets done printing, it just lets off.
Yeah.
And so you can push it back and forth. The direction command, there's, they're digital bits, so it's high and low. One way causes it to turn clockwise, the other one causes it to turn counterclockwise. It's the only difference. And then the pulse, I think it's on every rising edge. It makes it go one step. And in here's the controls that handles it, does all the phasing, and it's got a switch bank here on the end that you can choose the current, your drive current. So what you want to do is you want to use the least amount of current you can, but enough to meet your torque requirements. So you kind of look at your stepper motor data sheet and you say, oh, this is what I want on this, and you go flip 3 of the dip switches for that. And then the other 3 dip switches let you do what's called micro stepping. And micro stepping, I could be wrong, but you remember how we talked about here, I just turn this coil on and I turn this coil off, or I turn them both on and it chooses the position within a 1-step range, or maybe a half-step range. I think what they do is they PWM them and change the strength of the magnets. So you can choose 1-to-1, half step, quarter step, 16th step, I think all the way out to 64th of a step. So you could turn a motor, a lot of motors have like, they're spec'd in like 1.8 degrees per step, or 208 steps per revolution type numbers. You can do the micro stepping, and without having the gearing, you can turn that into 64 times 208 is 1,200, 1,300 steps per revolution. It's useful. It's more expensive, but if you're driving big hardware, hey, there's reasons why you use any different one compared to any other one. And it's an already prepackaged thing that you can just buy, and they're turning them out of China. I can go to eBay and buy them for $5, $10 each. I can go to Amazon and buy them brand new for $14 to $16 each. So if I'm wanting to build a CNC, or if I've got a big Bridgeport and I'm wanting to drive the table back and forth, I'm going to use something like that because it's big, it's heavy, industrial, it can move big things. So that's stepper motors. That's how they work. We talked about servos. Today was supposed to be servo, so we already did that. We're almost here 2 hours. So the homeworks for next week are, I want to be careful. I don't want to give you something that's amazingly bad. I do want you to homework 2, homework 3. So just as an idea, stepper 1 here, you're going to see all the code that I wrote for this. And it's a lot of code. It's simple, but it's a lot of lines. Missing, what's missing? I mean, it's not. Oh, something changed. That's odd. Fine, I'll go to stepper 3. Stepper 3, I took stepper 1 and I modified it to make stepper 3 so that it acts similar to the Arduino stepper library. So here's, we can sit down and watch this in a little bit, but let's see. This library that I wrote is to drive a stepper is 275 lines long, and it includes embedded case statements. So if you turn that into ifs, there'd be a shit ton of ifs, if-thens, and else's in here. But that will drive one. You can just look around. If you just Google Arduino servo software, you will see where a lot of people have written pretty much exactly this. They've gone through and made it all these millions of steps long and not folded it up nicely into something a little bit more concise. But you can see that. And next time I'll bring in both kinds of stepper motors and show you how to run them.
Okay, goes in there.
The other homework is my stepper 2 here. And this is just using the Arduino stepper library. So you see here it says stepper.h at the top, and basically doing the same thing with the stepper library. Again, I used a library. It took me 275 lines of code to have the same functionality as 3 lines of code. So,
Yeah. Sorry, libraries are good.
right, all that code's still there. Somebody else wrote it. It's hidden from me. I don't need to see how it works.
Yeah.
But I thought I'd dive in and play with it. What I want you to do is when you get it in, I've noticed a bug in the library that it doesn't work the way, for me, it doesn't work the way they say it ought to work.
Maybe you know too much.
No, I'm using their line. No, I'm just reading their instructions and doing what their instructions say. They have you encode. So that stepper library is intended to run that style of stepper that you've got there with the little card. And their code is it's C++ based again. So you instantiate a library. You call it a constructor, and the constructor is stepper. That's actually capitalized, stepper, I think. And whatever you want to name your stepper function. So if you use motor, and there might be some stuff that goes in it. And then you can say motor .rpm, I think is what it is. So this is a function in the class, or they don't call them functions in C++, a method.
That's what they call them in some other languages. I don't know about C++.
I don't remember. Once they pushed it from C up into C++, some of the things they changed what their names were. So, and I've always been ANSI C. I've written a couple of C++ things. But anyway, the motor RPM, you can put that in. So and then you say motor steps, or maybe it's step, and then you put the number in. So you'll have to look and see, is that for RPM, is that a byte, is that a car, is that an int, the right class of the right style, the right number of bits to put in. And for motor step, you put in, I want you to go 50 steps. So you say motor step 50, and it goes 1, 2, 3, 4, 5, 6, 50. And allegedly, if you put in minus 50, it'll go the other direction and give you 50 counterclockwise. So positive is, when you look at the face of the motor, when you look down at the motor and you've got the shaft sticking out in your face like this, when you're looking at it that way, this is clockwise, and counterclockwise is when you're looking down the shaft at the face of the motor.
Right. So that orientation.
Right. This orientation. So if this thing's turning this way, it's clockwise, and if it's turning that way, it's counterclockwise. So usually positive is clockwise and negative is counterclockwise. What I found is when I was using their library, it didn't matter what the sign I put in was, it went clockwise. I was like, well, that's not really useful. So I don't know what to do with it. I upgraded, I did some reading, and they said, oh, well, there were some things, and there's a newer upgrade, so I upgraded the library to what's supposed to be the latest library, and it didn't seem to make a difference. I want you to play with RPM. You'll find for the handwritten code that I did, works much better than the library. Me. I don't have a life. I'm going to sit down and write all this shit myself. I found that the fastest that I could turn the motor was about 17 RPM. Because it's so damn many steps. It's at 64 to 1 gear reduction. You got to go 2,000 steps to get one turn out of it. The minimum I could go, the minimum speed I could go was about 1.8 RPM. and the minimum speeds, because you're driving it off of that timer, right? And you've got to go through all, well, actually I was not driving it off of that timer. I was using direct digital writes. So that just means, you know, the time that it took me to go into that function, go through the if-thens to get there, fiddle those bits the right way, and then pop back out and then be ready to do it again.
Right.
I couldn't do it 2,048 times 1.8 times per second is about as fast as I could go on that guy. So fiddle around with it. Like I said, it's 10 lines of code total. Just play with the numbers yourself, hard code them in, see what happens. Tell me what you got. Did you get it to go both ways? And then we can look at it and say, well, how'd you do it? What made it work? You know, so I want you to understand what makes it work.
Sure.
And we'll do, and we'll figure out what speeds you're able to do, and then I'll show you my code again, and maybe a little bit, instead of saying, oh, it's 5 lines versus 750 lines. And there's things I could do. There are things I could do to speed up this code, but the way I've written it's very generic, which is part of why it's so slow. And I've using all the Arduino library function calls, so there's nothing special in there. There's no going down and directly fiddling bits and registers like I do in the servo stuff. So this one homework should take you less than an hour. If you were good and been doing this for a while, and you go watch that video, let me write this URL down. It is.
Looking at motors. Should find motor point.
It's YouTube. And it's B86. This is the URL. So if you just go straight to, if you search that, NQ DRDRSKVU. Do me a quick favor and type that into your YouTube and see if you get to the video or not.
I'm typing it in YouTube.
Nah, you have your browser up already. Is it capital U at the end?
Yes. Yes.
So B86.
Little N, little Q. I actually did proper-ish. You could tell I learned drafting originally because when I normally write, it's all block letters. Right?
Exactly.
28 BYJ stepper motor.
Yeah. That's your stepper motor, and he's gonna actually, he will tear that. He tears one of the motors apart and actually shows you this is how this thing works inside, and then he talks about the phasing of the steps and half wave stepping, full stepping, and half stepping, and how to do it. And if you kind of follow that, it's not hard to write a little loop that goes through, and you just say, okay, you know what? I'm going to do the four phase steps in 4 lines of code. Tell it to do it 100 million times with a delay between each one, and you'll be off to the races. Your motor will be sitting there spinning. You won't have any control over it, but it'll be doing a million steps. And
Rocking the gears.
yeah, understanding the gears.
Yes.
So he will, and that's like a 5-minute video, I think, maybe 6. And I think that's all we're going to talk about tonight. I think next time we'll go into analog and digital converters. I think that'll be useful. that's one of the last things that people, I mean, when we get into, you know, the maker world, things that we're doing just for S&Gs, stepper motors, servos, LEDs, ADCs. ADCs are for controls to drive things. Driving, you know, looking for buttons, which we talked about, and lighting lights, or just sending a signal out that we know is going to make something else happen. We talked about the H-bridge today, so how you would control an H-bridge. So we'll do that, and then, so next week I think we'll talk about A to D. So today is class 6. Next week will be class 7. And for class 8, bring me questions. Things, gee, you know, what do you think about, how would you do this? And I'll sit here and hum and haw about it for a few minutes, and then maybe draw some hardware up on the screen or on the board and say, this is what I would consider doing. It's not necessarily right, but this is my first thought. And then if we get into any components that we haven't used or talked about, then we can go off and figure those out. And we won't do those live. We'll maybe make that a class 9 or whatever it would be, and talk about that particular component.
Sounds good.
I've got 2 for you already.
What's that?
I've got 2 for you already.
What's that?
Oh, so one's basically a fancy thermostat to control composites cure cycles. So I don't know how up to speed you are on.
That's something we need to do. That is something that we might need to do. So I'm going to write these on here so that maybe when I go back and do.
Move this on video.
Yeah, I'll put it
Okay.
on. I want it recorded so when I come back and look at the video, I'll say, what the hell was I supposed to be doing? So we're going to talk about ADCs, analog to digital converters. An Arduino does not have a DAC built
Yeah,
in,
that guy was in there.
but you can get one digital to analog converter. It's the reverse function. So we'll talk about DACs, and that'll be talk only. We will, so next time. And then maybe the next time.
It just, it's
I know.
on top.
I'm looking.
We'll talk about I2C and SPI. And then maybe the, whoops, God, I dyslexified. Next time. We'll talk about Wi-Fi. Or Ethernet, or they're basically the same thing. I know I've got an Ethernet shield. I don't know if I've got a Wi-Fi shield or not. I might have to go buy one and play with it. Oh, we might also talk about LCDs somewhere, but they'll come after. They have to come after this. So. First thing you need to do is read temperature.
Yeah.
You can do that multiple ways
Thermocouple.
with a thermocouple. So that makes it a little bit more interesting. With a thermocouple, you need an ice reference, is what it's called. It's actually called an ice reference
Okay.
because it goes back to the way they used to do them. And you'll need the analog to digital conversion. And is it just simple bang bang type controlling, or is it
So
like on off?
yeah, with some logic, right? So you have the thermocouple telling the computer how hot it is. The computer knows the cure cycle that you want. So there's a ramp up time. Usually that's a specified, like, so many degrees per minute it warms up, and then you hold at this temperature for this amount of time, and then you ramp down at some rate, so many degrees per minute. It's always linear.
So the very first thing I'm going to tell you, I have a homemade solder oven at home.
Yeah.
And it has a process time that does something like this.
So you could call that a composite cure cycle.
Yeah, you heat up, get everything to a steady state temperature. You bake it for a while. This is called the ramp up. This is called the soak cycle. You soak it because when you go here, you're getting really hot. And you don't want to thermal shock everything going from here to here. So then you bring it up, and then this is a really short time, like maybe 25 seconds, and then it just turns it all off and lets the heat out. I was originally going to build this all to do this before. This was before Uno's and the whole Arduino ecosystem. I was going to build something to do that, and I started. Well, I need this controller. I need these parts. I need a thermocouple. I started throwing it all together, and I was $500 in parts for the thing. Now that we've got Arduinos, this has clearly gone down a lot.
Right.
And then a friend of mine's like, hey, you know what? There's these people over here, and you can go to Auber, A-U-B-E-R, Instruments, and they sell process controllers for, solid state relays, the heat sinks to go with the solid state relays, the K-type thermocouples, and I think I got a spare thermocouple.
I think most composites use J-type. I don't know.
They
the difference,
said they sell
but-
J-types also. It's
Right.
temperature ranges. It's
Okay.
temperature range.
Yeah.
Primary at the level that you care about, it's temperature range, and I got the whole thing for $300.
Yeah. I mean,
So,
we're talking about making an oven.
And it had all the software built into it.
Right.
Yeah, you can just
Yeah.
program in the curve. At this time, do this.
Right.
At this time, do that. At this next time, do this other thing. So for your process control, right, you break this up easily, right? You've got an oven, and you can only turn it on or off, right?
Yeah, I mean, I would assume that the heating elements have, some level of variance in them, but
They do, but what you find is you can't turn a knob. It's not like your oven. Even your oven at home, when you turn it to 400 degrees, it's got a thermocouple in there. It's got the equivalent. It's got a bimetallic strip. But when it gets a
Right.
certain hot, it just turns it off. It's called a bang bang control.
yeah.
So what happens is you're basically doing a PWM.
Yeah.
I turn it on all the way, and then when it gets where I want it, I turn it off, and it'll overshoot some, and then it'll come back down. And then when it starts getting too cold, you can hear them click, tink.
Right.
It turns that switch back on, and when it gets up above it, it tink, turns it off. And so you come up and you kind of do this
Right.
on your cycle, and this is the ripple that you just can't control because it's a bang bang system.
I think on the
But what you end up doing is basically PWM in
Yeah.
it, right? It's I turn it on, when I gets there, it turns off. So I end up seeing a square wave that looks like this.
But it averages.
Right.
Right.
And
Yeah.
I think on the 3D printer, do they call it PID? The kind of predictive.
PID is a PID loop. PID loop is proportional integral differential. And so purely proportional is this bang bang, on off,
Right.
on off, on off. And you get these things. Now you add in an integral term, and so we're going to get into control law here real quick. You have,
But that would probably be overkill for what he's trying to do, right?
right, so you have a driving signal and you have a feedback signal. And it gives you, so this is drive, this is error. This comes back into your process. And you take your, I guess the right way to do this is to go this way. And then your feedback comes here. Something like that. And so this would be what you're controlling is temperature. So you're pushing a signal out to control temperature. And your system can only turn on or off. So this is going to be on, off, or PWM at some rate to keep you where you want to be. The feedback is going to be the actual temperature. You get an error value that comes back and you act on the error. So if you're exactly on the error is 0, you do nothing. You sit there. But as soon as the error starts to grow, then you start to do things. So if you do pure bang bang, that's purely proportional. No error, no error, no error. Oh my God, there's an error, turn it on. Oh my God, I'm too hot, turn it off. Oh my God, I'm too cold, turn it on, right? On, off, bang, bang. And so the whole idea is bang to a rail, bang to a rail, bang to a rail. Now you can add an integral term, which is an average over time, right, effectively. And so that smooths things. It says, oh my God, I've turned on, but now I've already been on and things are going down, and I see that they're going down, and I don't want to do anything for a while. I'm going to let it go down. But if you do that, it stretches those things out over time, gets rid of this chatter, that's what they call it. But now you get maybe bigger dips. So then you add a differential, and the differential is the differential wants to bang bang. A small change does a lot. So you've got the integral trying to smooth it all out, and at the same time you see, oh, but we're going the wrong way. It's going to get colder and it's going to get cold fast. And it says, well, okay, I'll start turning it back on, but I won't turn it on as hard because this thing's smoothing me out. And the process controllers build all that into them.
Yeah.
And you can spend a lot of time building one of these and getting it right. And,
Right.
But that said, your process control is we'll call it an Uno for shits and giggles, and you're going to have one bit that comes out and runs a solid state relay, depending on what kind of oven it is, that is going to take hot off your wall, and it's going to run it out
To your heating element.
to the heating element,
Yeah.
which is going to go back to neutral, and this will have a line that comes back here to ground
Yeah.
in this guy, and then you will have an ice reference, which has 2 wires that go to the thermocouple. I don't remember what the symbol for a thermocouple. Oh, I do. It goes to the thermocouple. A thermocouple, the symbol is this. And that's inside your oven. And then that comes back 2 wires, or maybe 3 that are powered. And one of these will be, this is the symbol for an analog to digital converter.
Okay.
Which is built inside of there. There's a 10-bit ADC in there, and you'll only need 8 probably.
So when you say ice reference, you literally mean like a cube of ice.
That's actually what they used to use. It's called an ice reference because when they first started dealing with these, I want to say it's called the Sebring effect. They would actually have a wooden bucket full of ice, and they'd bring them in. Most people don't understand how a thermocouple works. They think they understand.
I probably don't.
Well, and not to get too deep either, but thermocouple versus thermistor.
Yeah. So here we go.
Okay.
A thermistor, which is what most people think a thermocouple is, has a. So if I think about a pot, right, a potentiometer, I would draw it like this. And the very first class we talked about a resistive divider, right?
Yeah.
I've got V to ground, I've got R1, I've got R2, V out equals R2 over R1 plus R2 times V.
Yeah, where's your V out? Off that
Right here.
tree, right?
Right here. So what a potentiometer is physically, often it is a coiled up wire with some resistance, and it actually has a little metal wiper that slides across that wire.
Right.
So as it slides, pictorially it comes up here, so it's there, or it comes down here, so it's there. So you can come all the way down to basically 0, or you can come all the way up here to 10K or whatever the value is.
Right.
So a rheostat, that's what they used to call them, a variable resistor, is effectively this very same thing that is tied like that. So if I come all the way down here, it shorts across and the end-to-end resistance is 0 ohms. If I bring it all the way up here, then it's effectively the whole resistor, so the end-to-end resistance is the whole value, and if it's halfway in between. Imagine that a thermistor is one of these, that the driving force here is temperature. It's all in the chemical compounds inside of it, and excitation values, and
Yeah, no, my 3D printer has a 100K.
it has a PT1000 on it, or a PT100 is what they usually use, and that's usually, I think a PT1000 is actually 1,000 ohms, and a PT100 is actually 100 ohms. I think it's 1K. Because 100K, there's too much noise. 100K, you want it. And the trade-off with this thing is if it's too big of a resistance, then any little
Right.
noise from anywhere makes
Sure.
it, even thermal noise becomes a problem at that level. So this is a thermistor, and the hottest thermistor I've ever seen is maybe, they can go up to boiling, 200 or 300 degrees Fahrenheit.
That was my rudimentary understanding, was that your thermistor is good up to a fairly low
a relatively
temperature.
low temperature.
Yeah, or
If you're curing epoxy, thermistor's fine. If you're curing,
No, I mean if you're gonna, if you oven cure, the reason you would set this up is to make an oven to use advanced resin systems like prepregs and
so
stuff
for
like
circuit
that.
boards
So,
and shit like that,
um,
or ceramics even. If you're doing ceramics, then you're up into the 1500 degree C range, and
yeah, I mean, so for like most, I think the prepregs that I would play with for out of autoclave carbon composites, they typically have like you have an option of the cure cycles, right? So whatever your hold temperature is affects how long you have to hold it there, and like 150 degrees C, or maybe it's over 100 degrees C.
well,
And then you can get up to like 250 or 350 degrees C.
right. So you've got other issues.
Wow.
The hottest I've seen thermistors that'll go that hot,
Mm-hmm.
but they're expensive.
I mean, I know for a fact that they use thermocouples.
No.
Yeah.
Where I'm going is thermocouples are cheaper
Right.
for that type of thing, and there's a two-way problem there with getting crap into your process. Right, most of the thermistors are wrapped in epoxy, and it'll outgas into your process, and it can screw up your process. And vice versa, that epoxy cures at about the same temperature as what you're doing,
Right.
and your epoxy process can then screw up the thermistor, and then it might not be any good after the next process, and you have to change it out and whatever. Thermocouples, when you buy that kind, are almost always encased in stainless steel.
Yeah, and then we wrap them in flash tape to put them next to the laminate.
Right. So
So they're effectively sealed from
Yeah.
the product.
So the next kind is a semiconductor. There's actually semiconductor, and you can buy those, And that's what brought it up for me to think about, you can get them as SPI or I2C bus. So you talk to them digitally, and you give them a power line, a ground line, and a single bit, and you toggle the bit. It's actually, I guess it's 4 wires on a lot of them, because the way it works, it's a serial bus that pushes through and pushes out, so you can push your data in and then read it back out the other side. Unless it's I2C, and then that's, if it's SPI, it's a 2-wire bus. If it's I2C, it's a 1-wire bus. And they can talk on the same wire, and there's a way that they know who's talking. There's a master-slave relationship there. So for a thermocouple, the drawing actually explains what it is. It's 2 wires welded together, and the 2 wires are made out of a different metal. And this is called, I think, the Sebring effect. If you have two dissimilar metals and you weld them together, that's a weld. Let's back off. Any one metal has a Sebring effect. If I change the temperature on this end, it's going to have a change in potential voltage across it. And that's because of a change in electron mobility due to temperature between the 2 ends. But if I have a piece of copper wire, and I tie this to ground as a reference, and I have some fancy way of measuring voltage here, and I put a flame right here, I'm going to see a voltage change. If I put the flame here, I'll see a voltage change, but only because the heat travels up here. This is really weird. If I take this wire and I loop it back all the way to here and do the volt reading there, I will read 0 volts, because these 2 points are at the same temperature, the distance is the same, and so the change in temperature over length is identical between the 2 wires. So that's why I run in a second wire of some other material that has a different Sebring value.
Right.
So this one end to end raises 1.2 volts, this one end to end raises 1 volt. And so I get a 0.2 volt change in temperature. And often you'll see, I think, copper and captan. Damn, what's that material called? Capstan? Captan? I can't think of what it's called right now. But that's the difference between a J, a K, an L? No, you skip L. Now, there's 4 basic types of thermocouples, and what they are is different metals.
Right.
And it has to do, if you're doing a really hot temperature process, you'll melt your copper, so you use a different one.
Right.
And 90%, that's 90% of it. But what happens is, as my room temperature changes, I'm changing the temperature end to end.
Mm-hmm.
So that means that the voltage I see here changes. So they used to use an ice bath, because if you've got a bath of melting ice, it's exactly 0 degrees C, right?
Yeah.
So it's called an ice reference, and Analog Devices makes them, TI makes them, all your major semiconductor people who deal with analog stuff make them. Mm. And it's a semiconductor that goes in here, and it's all temperature compensated, and across reasonable temperatures that you would normally see somewhere, industrial, maybe -20 to plus 85 centigrade, and it handles that.
Right.
I can't tell you exactly how it handles that. It just,
It's good enough for me.
it's a black box and it handles it, and it is called an ice reference.
All right.
So go read about an ice reference, go Google ice reference and thermocouples, and you can find tons of stuff on what an ice reference is. And if you just hook up an ice reference if you just hook it up directly without an ice reference, your process control feedback, the temperature you read will drift with the temperature in the room that you're in.
Okay.
And what the ice reference does is they're figuring that if you're going through all the trouble to put a thermocouple on here, you actually want to know what the temperature really is.
Yeah. Not just that it changed.
Not just that. Well, yeah. What could happen is the room starts getting warm, and that means that the difference in temperature is going down if you're heating an oven, right?
Mm-hmm.
And so the control system thinks, oh, it's getting too hot in there. I'm going to dial it down. If you're smoking a ham, it's not going to matter, right?
Yeah.
10 degrees probably isn't going to make a whole hell of a lot of difference in how good your ham tastes. But if you're curing an epoxy that's going to want, oh my God, I need to be at plus or minus a half a degree for 3 days, or it's all broken, you're going to end up with broken epoxy, right? Your carbon fiber is not going to be laminated the way you wanted it laminated.
Exactly.
So that's what the ice reference does.
All right. Yeah.
So the nice thing is, if you go to Auber Instruments and you buy one of these things, it's got all this shit built into it.
Right.
And it has the thing, instead of you having to go figure out the PID curves and all this shit on your own, you can tune them right there and say, look, I want this value to be this and this value to be this. And you set up a time temperature table. At 0 seconds, I want it to be this temperature. This is my assumed start temperature. At 15 seconds in, I want it to go to this temperature. And at 15 seconds, it'll start ramping up to that temperature. And at 30 seconds in, I give it the same temperature again, and it stabilizes, and it'll try to hold it there. And it's already made. It's got a J-type and a K-type thermocouple input, so you can just choose this one or that one.
And multiple thermocouples? I'm sure.
I think it can handle. The one I bought can handle 2 separate thermocouples, but it only reads one. It can be used with a J or it can be used with a K.
Uh-huh.
And it has one single process control temperature that it listens to.
But like if I wanted to put 6 J-types.
Oh, okay. Well, on this one, you'd have to buy 6 of these things and control each one separately.
Yeah.
So yeah, so then maybe it makes more sense to go do this.
I don't know.
So yeah, I've done this before. Mine's simple, right? I've got one thing that I want to control and heat and cool and heat. So, but now if you get into now, all right, and you're going to spend a lot of time in software writing your PID loop.
The
Loops, because you'll have one for each one, right? If they're assuming they're all different.
What I was going to say is the firmware for my printer has a PID tuning function where I think it goes full bore and then measures the thermal drop off and figures out what the characteristics are. So anytime you make any kind of change to the hot end of the 3D printer, you just do the PID tuning and it figures out what that curve is for you.
So I've used some different fun instruments. I'm shutting this thing off now.